Welcome to Basic Physics Laboratory, Module 11, Segment 3, Standing Waves on a String. So for this video outline, 1. Purpose, 2. Basic theory, 3. Data and processing, and 4. Report format. The purpose of Practicum Module 11, Standing Waves on String are: first, determines the harmonic frequency due to standing wave on the string. Second, determines the velocity of standing waves on the string. And third, determines factors that affect the velocity of standing wave on the string. So we will go on to the basic theory. So a wave is a vibration that propagates in a medium, which carries energy from one place to another, and is not followed by the movement of the intermediate particles. If a string with a certain tension is vibrated continuously, it will be seen as a waveform whose direction of vibration is perpendicular to the direction of wave propagation. So we call this wave as transverse waves. If both ends are closed, then the waves on the rope will bounce and can produce stationary waves that appear in the form of nodes and belly waves. So in this experiment, we will using the Meadows experiment design as follows. So this Meadows experiment design. So there is a string, a vibrator. So the vibrator will vibrate the string, and then in both ends it will be closed. So there's a pulley here, and there is a load in here. Okay, and then we'll go on to the stationary waves, also known as standing waves, or stationary waves. Are waves formed by the combination or interference of two waves that have the same amplitude and frequency but have opposite direction of propagations. So there is a waves from here, and then the waves will bounce and it will interference, make us stationary waves. So in general, the velocity of stationary waves can be found by the equation v is equal to lambda times f. The v is the velocity of the waves, and then the lambda is the wavelength, and the f is the frequency. From Meldal's experiment, the velocity of wave propagation is found by the equation v is equal to square root of f divided by mu. So v is the velocity, and then the f is the load, and then the mu is the density mass of the string. And then we go on to the data and processing. So from the table 1, data from the measurement of string mass and string length. So we use some string, so there is thick, thin, brown, and green. It has its own mass. We measure both mass and the length. And then we calculate the density mass. So we divided mass divided by the length. And then the second table is the result from the load mass experiment measurements. So there's the load mass in hook, mass 1, mass 2, mass 3, and so on. So we measure the mass. And then for the experiment 1, determining harmonic frequency. So this is table 3 experiment data of thick string harmonic frequency. So we measure the frequency. The first harmonic frequency, second harmonic frequency, third harmonic frequency, and the fourth harmonic frequency. And then we calculate the 1 over f. And then we also measure the lambda, the wavelength, and then the a is the amplitude. And then we calculate the velocity. The velocity is with the wavelength times the frequency. Okay, and then we calculate the effect velocity and the standard deviation. And we are using the formula lambda is equal to v times 1 over f. So we are using this formula to make the linear regression. Okay, so the y-axis is the lambda or the wavelength, and then the x-axis is 1 over f or the wave period. Okay, so in here we can see that the y is the wavelength and the x is the wave period, and then we can use the linear regression like this. Okay, so we will get the regression equation. So the y is equal to something x at plus constant. Okay, and then the coefficient behind the x is we call the phi experiment. Okay, do the same steps to find the phi average and the phi experiments for other strings. Okay, and then we go on to the experiment 2. Factors influencing wave propagation speed. So this is the table for standing wave experimental source data on tick string. So this is on the tick string. So we measure the frequency and then calculate the period is the 1 over f, 1 over the frequency. And then for the mass, we are using the table 2. Okay, and then the lambda, we measure that. And then for the f is we calculate by mass times the gravity acceleration. And then for the velocity, we times the frequency and the lambda. Okay, and then for the v squared, we just v times v. Okay, next we will determine the density of the tick string by using the formula F is equal to mu times v squared. Okay, so we will use the linear regression. So the y-axis is the F, and then the x-axis the v squared. So like this, the F is the tension force, and then in the x is the square of propagation speed. So we will get the linear regression like here. So we will obtain the equation, the y equal to something x plus constant. So the coefficient of the x is the mu experiment. And then we can determine the error between the mu experiment and the mu tick, or the mu string that we use. So the error is mu experiment minus mu reference divided by mu reference times 100%. Okay, we will get the error. Okay, do the same steps to find the mu experiment and error for other strings. Okay, so that's all for this video. Thank you for watching.